A major dam stands between a reservoir and a valley, holding back water masses measured in billions of tons. It looks like a wall, but structurally it is a force-routing machine that transforms water pressure into controlled compression and ground reaction. Water pressure grows with depth. Near the surface, force is small. Near the base, it is much higher. That creates a triangular pressure distribution, resulting in a large horizontal push and an overturning moment at the foundation. A gravity dam resists water mainly with mass. Its thick concrete body keeps the resultant force inside the base, so the structure stays in compression and avoids tension cracking. In simple terms, it stays put because it is very, very heavy. Arch dams use geometry more than mass. The curved plan shape pushes water loads sideways into canyon walls. Compression flows along the arch to abutments, allowing thinner sections where rock conditions are strong and stable. Designers must prevent sliding at the base and uplift pressure under the dam. Drainage galleries, grout curtains, and foundation treatment reduce seepage and pour pressure so friction and shear resistance remain reliable over decades. Dams are not meant to hold all flood water indefinitely. Spillways safely release excess flow, keeping reservoir levels within design limits and reducing extreme loads on the main structure during major inflow events. Mass concrete generates heat while curing, then cools and shrinks. Without planning, that can cause cracking. Engineers place concrete in lifts, use cooling pipes, and control mixed design to manage thermal gradients and long-term strain. In seismic regions, dams are checked for earthquake-induced inertia and hydrodynamic pressure. Models simulate dam, reservoir, and foundation interaction so movement stays within acceptable limits and critical sections maintain capacity. Large dams are instrumented for decades. Piezometers track water pressure, pendulums and GNSS track movement, and strain sensors track stress trends. Performance is compared with predictions to detect change long before it becomes risk. The design life of a dam depends on maintenance, gate upgrades, concrete repairs, seepage control, and periodic safety reviews. Structural integrity is not a one-time achievement. It is an ongoing engineering program. Water pressure pushes the upstream face. The dam redirects that force into weight, geometry, and foundation reactions. Spillways manage extremes, drains manage uplift, and monitoring validates behavior. That is how a static wall becomes a dynamic safety system. Dams are among the largest structures humans build, and they work by respecting force, flow, and time. This is load-bearing, engineering explained through the paths forces take.